Okay. The last topic that we'll look at this week is topic 9.4 on imaging resolution. It's a little bit of a strange topic because we don't actually look much at imaging. And so understanding the limits of imaging due to diffraction is kind of a little bit strange, but we'll charge ahead anyway. I'm going to start by introducing you to the most basic form of imaging, which is a pinhole camera, also known as a camera obscura. The way that these are set up is that you have a darkened room with a small hole inside of the wall. A lot of science museums have these, and if you ever get the chance to see one work, I highly recommend it. Light from outside can follow a straight line path through this little hole in the wall. But depending on where the light is coming from, the straight line path from that object through the hole and reaching a blank wall is slightly different. So, for example, the top of this urn, the light to travel through this hole would end up following a straight line path close to the floor. On the other hand, near the bottom where this person is sitting, the light would follow a path through the hole and end up above. As a result, the light that shows up on the wall will produce an image of what is outside, that is, in this case, upside down. And the key thing here is that because the production of this image involves light passing through a small aperture, diffraction plays an important role in how clear this image will occur. And you might say, well, that's of limited use because we have almost no pinhole cameras anymore that we use. Well, your eye operates in much the same way. The dilation of your pupil serves the same role as the hole in the wall here, albeit slightly modified by the lens that's in your eye as well. And on your phone, you have very narrow apertures as well that light has to pass through on its way to an imaging surface. And so, though the pinhole camera is a particularly simple tool for projecting an image, almost all imaging tools involve a circular aperture of some sort, whether that's a lens like a glass, or your pupil like an eye, or even a large telescope like the Hubble telescope or that's in outer space. All of them involve apertures of some sort. And that's going to lead to the diffraction of the light that prevents us from resolving images. So, because diffraction through an aperture causes the light to spread out, this can effectively blur an image. Here at the top of the screen, I've got several pairs of lines. The lines are all exactly the same size, but you'll notice that if you're standing far away from the screen, you won't be able to distinguish them at some point. The size of the lines and the diffraction that occurs with your eye causes them to broaden out so much that they essentially overlap. And your eye and your brain can't tell them apart as two separate lines. If you're 2 to 3 meters away, you're almost certainly going to be able to resolve these on the right, but you probably won't be able to resolve the ones on the left. And depending on sort of the quality of the lens in your eye, you and the quality of the compression that YouTube makes, you won't be able to distinguish maybe this one or this one, right? So that's what we mean by resolving two different objects in an image. This is more often drawn with 2 point sources. These might be 2 points of light that are infinitely small, like two stars very, very far away. But the diffraction that occurs spreads those out so that they gain this finite size when you take a picture of them. And if that finite size ends up being much larger than the separation of them, you won't be able to tell that there are two stars there at all. We can in this image, but we can't here tell that there are two different points located here and here. They're just too close together to resolve. When we talk about resolving images, there's something known as the Rayleigh criteria. So the images at the left show the diffraction pattern for two different objects. We're going to assume that they're just one color of light. And so this is a monochromatic diffraction pattern. We see that these objects are separated. One is on the left at about 0.35 net 0.035 radians to the left. One is 0.035 radians to the right. And we can see the diffraction pattern in red here. It looks like it's spreading out maybe, I don't know, maybe a little bit 0.035 or something like that, right? For the first maxima or first minima to the left and first minima to the right. And this one's way over here. And we can see the sum of those two in purple. And it's clear that we can see two different point sources creating two different diffraction patterns. On the other hand, down at the bottom, these are separated only about a hundredth of a radian on the left, a hundredth of a radian on the right, and the diffraction is so strong that the sum of the two looks like there's actually just one object that's brighter located in the middle. These are not resolvable. The Rayleigh criteria is that the diffraction pattern from the left object has a minimum at the location of the central maxima on the right, and that this is the limit of what is just resolvable by the eye. So here we can see the central maxima, and directly below it we have the first minima from the object on the right, the minima from the object on the left, and above it the maxima on the right. And the purple curve shows a distinct dip in between those two, which means that it's just resolvable. Really great video showing the transition between resolved and irresolvable images here. I highly recommend you pause, find that link, and watch this video of two students doing an experiment. In order to describe the Rayleigh criteria for resolvability, we need to know what the angular separation means carefully. Angular separation is defined as the ratio between the separation of objects and the distance to them. We're always going to be working with a small angle approximation here. Nobody has trouble resolving things that are large angles apart from each other. It's always going to be a small angle approximation. So the arc length and the distance are basically the same as the linear separation and this distance. So the angular separation of two objects that are far away from your observing location here on the left is this angle here, which is the separation of the objects, in this case, two stars, and the distance d to that point. Similarly, if we look at a diffraction pattern, we can define the angular location or the angle of diffraction, which we've done before. Angle of diffraction is lambda over b. When we look at, this is where we get into a little bit of a detail. Most of the apertures that we care about with imaging are not slits. They are circular apertures. Your eye, telescope, mirror, camera light, pinhole camera. And the diffraction minima isn't actually located at lambda over b. It actually ends up being at 1.22 lambda over b, where b is the diameter of the hole. So you'll often see this coefficient of 1.22 that shows up for the angular separate, or the angle of diffraction. That's because we're looking at a circular aperture. That's where that 1.22 comes from. And so the Rayleigh criteria then, that the diffraction minima shows up underneath the maximum here, is that the angular separation, theta A, S over D, must be greater than or equal to the diffraction angle, theta D, 1.22 lambda over B, for a circular aperture. And so this is what we know as our Rayleigh criteria, and it's how we know if two objects that are separated by some distance a long ways away from us will be resolvable or not. You can go back to looking at the two lines here that you can just resolve from a distance of 2 to 3 meters. You can find their angular separation by looking at the distance between the lines and dividing by the distance you're standing away from the screen. And you can use that to figure out when you can just resolve them. That will tell you something about uh, the aperture of your eye, right? Especially if we assume that the wavelength of light is something like green, or something like that. Problem solving that involve the Rayleigh criteria on resolution the only real trick is making sure that you have some sense as to what the diameter of the aperture is, and making sure you're comfortable thinking about how distances like the separation and the distance to an object translate into an angular separation. So here's two examples to play around with, one related to that simulation where you can estimate your pupil size, and one related to the Hubble Space Telescope with its primary mirror of 2.4 meters. In this case, it's saying what is the angle between two just resolvable points of light, perhaps two stars, when the wavelength of light is 550 nanometers. In this case, we know that the aperture is 2.4 meters in diameter, so we can find the angle of diffraction as 1.22 times 550 nanometers divided by 2.4 meters. It's going to be an extraordinarily small number. And that is the same thing as the ratio of the separation of two stars to the distance away. So here's a picture of, say, two stars that are 12 million light years away. So how close together could they be and still be resolved? Also on the topic of resolution, but quite unrelated to this type of imaging, is the idea of a diffraction gratings resolution. When we talk about a diffraction grating resolution, we're talking about using a diffraction grating to create a rainbow that sorts out all of the different colors of light that are present in white light. Because the angle of diffraction, you have your equation n lambda equals d sine theta. The angle of the angle to that interference fringe for different colors of light is different based on their wavelength. Diffraction gratings can separate light into its colors. This is super important for astronomers who use this to find the spectrum of different stars, which can help them to figure out if they're moving towards us or away from us, or the chemical composition of those stars. The resolution of a grating tells you how well you can identify individual frequencies. These both show the full spectrum from a diffraction grating, but the second image has a much higher resolution. You can see this with the sodium D line, which is a special transition in sodium that's clear from many different stars and also in our atmosphere. These two black lines right here are not resolvable with this diffraction grating. On the other hand, down below, these two lines show up as far apart, and in fact, we can see additional structure in between them because of the high quality of the diffraction grating that's been used. So this is a different way of describing resolution, is how close together in wavelength can two colors of light be and still be observed to be separate in the spectrum created by a diffraction grating. So same word, very different phenomena that we're looking at. In this case, we aren't going to derive an expression for it. I'm just going to give it to you. Similarly, it will be given to you inside of your data booklet. The resolving power of a diffraction grating is defined as the ratio of the average wavelength between two neighboring lines to the difference in their wavelength. So the average value divided by the difference in value. And then that is equal to for the nth order diffraction, when you have n lines of your diffraction grating illuminated, this equation is true. The resolving power is equal to the average divided by the change in wavelength that can be resolved is equal to m, the order of diffraction, meaning 1 or 2 or 3. and n is the number of lines in your diffraction grating that are illuminated. Typical problems you can see inside of your textbook. Very short topic, really only 2 types of problems, and hopefully we'll see some demos of these when I get back to class. Take care.